All right, so welcome to the nexMPI training school here at Prague. First of all, you look awesome. It's a fantastic view here with this lecture hall. So my name is Jochen Franke. I'm the product manager for magnetic particle imaging at Bruker Biospin in Germany, in Ettlingen. And today I have two talks. The first talk, which will be given right now, is about spatial encoding schemes and especially the difference between field-free point, FFP, versus FFL field-free line. I need to declare I'm an employee of Bruker. And let's getting started into the basics of MPI. And before I forget, as soon as something is unclear, please raise your hand. It should be an interactive session here, okay? So that you make the most out of it. All right, so signal generation. What do we do with the magnetic particles? These we are exciting with an oscillating magnetic field, which is given here in different color codes. The excitation is provided by the so-called drive field. And if we are looking for, so this is the oscillating magnetic field over time, the drive field. And now what we are doing, we drive the magnetization of the particles into saturation. And due to this nonlinear response, the magnetization over time is no longer just a sine wave, so it does not follow exactly our external magnetic field, but it's more a kind of a boxcar function, and therefore it introduced not only the frequency which we inject, so the fundamental 25 kilohertz for instance, but also provides some harmonics due to the nonlinear distortion based on this nonlinear response. Okay. In order to acquire this signal, the particle signal itself, we need to make sure, first of all, that this drive field sine wave is a perfect sine wave, that it does not have any distortions in itself. Okay? Therefore, we have a power amplifier and we have a bandpass filter specifically tuned to the excitation frequency. So then we have this perfect sine wave here in red. This goes to our transmit coil, and then the receive signal, which is the derivative of the magnetization of the particles, will be tapped. But we also have a feed through from the transmit to receive, as we need to acquire instantaneously during data particle excitation and reception. So this is at the very same time. Therefore, we need to introduce a band stop filter, again tuned to the basic frequency of the drive field. So what happens in the spectra though, we filter out the fundamental frequency, and what is left over are the harmonics, which is the fingerprint of our particles. Right? So this is a basic concept of signal generation in MPI, or first of all, magnetic particle spectroscopy. So if we zoom in now into the particles, what happens if we have an oscillating magnetic field? First of all, these superparamagnetic iron oxides are random orientated in the field of view, and by applying this oscillating magnetic field, they align along the magnetic fields and will point to the very same direction. Okay? But bear in mind, the particle signal itself is really, really tiny. So we are talking about nanovolts to microvolts only, and the drive field excitation is a many-fold magnitude higher compared to the receive signal. So there is urgent in order to make the system round out in order to measure the particle signals simultaneously to the transmit signal. As we are talking about magnetic particle imaging, we need a kind of a spatial encoding, right? So we don't want to characterize the particles only. We want to measure the distribution over space. So what we can do, we can take two magnets facing with the same polarity to each other, forming this magnetic gradient field. And I have brought kind of a similar representation here in hardware. And what you can see is that these fields cancel each other at the very center. And this is called the field tree point, or generally the field tree region. Okay. Now, with having an oscillating magnetic field, and the particles located here, we are driving through this magnetization curve in a centered way, and therefore the magnetization is also kind of centered. If we have particles away from the field tree, from the origin of the field tree point, we drive through the magnetization curve of the particles non-symmetrically, and therefore the magnetization response over time looks differently according to their position. And exactly this is what we are exploding for image reconstruction. So what you can see is here the time course of the magnetization for different points in space, the induced signal, which is a derivative of this magnetization curve, which looks differently, and last but not least, the spectrum of these particles or of this induced signal, which is just a Fourier transform of the time signal. Okay, and what you can appreciate if we are at the center region, we only have the odd harmonics. Yeah, so the third, the fifth, and so on harmonic. While if we have an offset and we drive through the magnetization in a non-symmetric way, we do have the odd and the even harmonics. And this is exactly the fingerprint which we are exploding for image reconstruction at a later stage. So now we consider three particles sitting here, the blue, the red, and the green one. And what we do, we have this gradient field and the field tree point, which is moved by the the drive field coil, the drive field, from here to here. Okay, and now you can see, first of all, this is a drive field excitation. It's a cosine representation now, and we induce signals at different time points. So now, and this is recorded by the system. Now we concentrate on this part. What we next do, we transform the coordinate system along not at the time. Now the time is in this direction, here the voltage. And now we need to spread the signal according to the point in space where the drive field or the field tree point is located at a given time point. And then we need to correct for slew rates, as it's not a continuous movement of the field tree point. It's a sine wave or a cosine wave, and therefore the velocity of the field tree point is differently depending on the position, and this needs to be compensated. These 3 points are expected to have the same concentration, and therefore they are expected to have the same amplitude of the voltage, which they don't, right? So by correcting for the slew rate of the drive field, we can adapt the signal intensity accordingly to make MPI again to be quantitative. And last but not least, we transform this induced signal and this corrected signal into grayscale to be in the image domain. So this is just a single line scan. So now consider we have a phantom and we do this line scanning as just described. So we go through with the field tree point, acquire the data, make the corrections, and plot in grayscale. And this step by step in line scanning mode. So you can see that we can reconstruct at the end a phantom or the image which we have placed in our magnetic particle imaging system. So this is a very straightforward model by just plotting the signal intensity over time. This is called the X-space reconstruction approach, and this is very easy to be done on a 1D excitation. But it's in 1D it's quite slow, right? So what we want to do is to acquire the field of view in a more rapid way, and therefore we have not only one Helmholtz coil for having a homogeneous magnetic field, tri-field, but we have two of them orthogonally to each other. And now we can drive this field-free point in space not on just a line, but on a so-called Lissajous trajectory. So this is showing just the center of the field-free point. So this trajectory spans up, first of all, our field of view, and it excites the full particles within the field of view. Okay. But yeah, just plotting the induced voltage over time according to the position in space is no longer very straightforward. That's why we are not only talking about the time series, but we are talking about, so this would be the time series. So you can't appreciate the three different points, right? As we have a crosstalk by these particles. So what we are using is to transfer the time signal into frequency space, so to have the spectra, so the voltage over frequency, and now we can appreciate the two different frequencies injected for X and Y, and the harmonics originating from these ones. Now having a spectra does not help either. So what we do, we make a reconstruction based on a system matrix. A system matrix consists of a series of data points acquired for each point in space which we want to reconstruct. We put a point source at this given point and record the response of the particles. And this we do for each point in space, and this spans up, so to speak, our system matrix. Now, as MPI is quantitative, we can formulate an equation which is called the system matrix time the concentration of the particle equals to the induced received signal. Okay? Straightforward? No, not really, as the system matrix itself is in a poor condition, and therefore we need to, we can't inverse the system matrix easily. That's why we need to use a regularized reconstruction approach. Here you see the L2 norm, and this can be solved by the Kachma algorithm.
And when the previous slide we had like a continuous path that we make, and now we have a discretized matrix.
Yeah.
Do you then first discretize also the continuous line into steps to overlay the two? No. So we still stick to this trajectory, but we tap for this point, this point, this point, this point, and this point, and we run the full trajectory for each point in space. Okay. So we run this sequence, this trajectory for each point individually. Okay, and then we have the basis data for the reconstruction, the so-called system matrix. And this system matrix does not only contain the fingerprint per position, but it really contains the physical properties of the particles. So it's not a model which we apply, it's really a measured procedure. It's a tedious procedure, this is for sure, but it contains the true response of your particles. All right, and so now we have a distribution of particles. We now need to combine the system matrices accordingly to have the same signal as we receive. So minimizing the error between the to be reconstructed concentration times the system matrix with subtracting the received signal. This should be in ideally 0, and then we have found our distribution in space. So a schematic block diagram of a full MPI system would look like that. We have already seen. So we have a power amplifier for the tri-field, a bandpass filter, the transmit pass or the transmit coil, a receive coil, a band stop filter to filter out the fundamental frequency,
a low noise amplifier, and then we are going to digitize the time signal. Then for spatial encoding, we are using, again, a power amplifier, a low pass filter, and the so-called selection field. And this could be either a permanent magnet just making a field point. Then we don't hear about any power amplifiers, or these are made by electromagnetic coils. And last but not least, and this I did not touch so far, we can extend our field of view by a different set of coils. And these are called focus or shift field coils, depending on which vendor you are talking to. And these ones are, again, like they transmit the tri-field coil, a homogeneous magnetic field, to shift the entire magnetic gradient into one or two or even three directions. Okay, and these ones are more in DC, so in constant values, to low frequencies, as we need to deal with very high inductance. So this is at 25 kilohertz. The tri-field selection field could be static, and the focus field are quasi-static, so very low frequencies to shift the entire field of view. Okay. So this is the product which you will see today here at CAPI. So this was one of the first, or it is the very first commercialized MPI system here in Prague. I think it was the third installation, if I'm right. Yeah, made by Bruker. And now I would like to give you some details about the structure inside. So what we have is a magnetic electromagnet for the selection field. So this can be adjusted from 0 Tesla per meter to 2.5 Tesla per meter. And then we have the 3-axis tri-field coil in the center, which we don't see in this representation. It is tuned for 25 kilohertz in our case. It can be adjusted from 0 to 14 millitesla peak to peak. And it allows for a 12 centimeter object to be hosted in this system. Additionally, we have a 3-axis tri-field focus field coil to shift the field of view in the 3 orthogonal directions. And as we have 12 centimeter, which is this size roughly, we can make use of having dedicated inserts, so-called inserts, to make the MPI system even more sensitive to our precious magnetic particles. So here we have a representation of the signal intensity, or the transfer function of our transmit-receive coil, the built-in transmit-receive coil, and a dedicated receive coil, which can be included in the system case by case. So, and here we have more than 20 dB difference in signal intensity. So we can tap the MPI signal, which is very tiny, in a much more efficient and more sensitive way. And this is not only good for just having a better SNR to reconstruct images with lower noises, but it also applies to a very lower limit of detection. So by the built-in transmit-receive coil, we are able, this is a result from our customer in Aachen, can reconstruct or detect and reconstruct 58 nanograms in a voxel or in a vial for the different positions, while with the receive-only coil we can go down to 8.5 nanogram even. Okay, and this is a real game changer. So if you are interested, I propose you to go to this paper, reading all the different stuff, how this coil was built and how the measurements have been performed. And what you can see here again, so this is the signal background of the receive-only coil during tri-field excitation. So the noise floor is at minus 130 dBm. Okay, and in purple and yellow there are different traces in the field of view. 1 microliter of CyanoMac-D or 8 microliter CyanoMac-D. So you can appreciate more than 100 dB C difference from background to the MPI signal. And this is the difference what we can leverage for reconstruction. So now, point imaging is pointless, right? It just shows the limit of detection. We really want to do applications, and I have brought a couple of different applications which we and our customers have performed in the recent years. So it ranges from molecular imaging to cell tracking, inflammation detection and staging, to cardiovascular imaging and neuroimaging, to nanotech research, optimizing the particles for having a better magnetization curve, a steeper magnetization curve, or more broader hysteresis, which will be the next topic in my next talk. And last but not least, the hot topic and my favorite one, combining magnetic particle imaging with magnetic fluid hypothermia to be a theranostic system. So what you can see here is a time lapse of a real-time bolus acquisition of a beating red heart. This is basically my PhD result made in Ettlingen. It's a hybrid system. It's acquired on a hybrid system combining MPI and MRI in a single device, and by a bolus of 21 microliter of, in this time it was still Resolvist, we can acquire the different heart chambers in real time with a time resolution of 21 milliseconds per volume. Okay, so to really have a real-time signal response. Here you can see a so-called multicolor reconstruction for 2 different tracer types, and this is a result from our customer in Hamburg. So they injected Perimac and LS08, so 2 different very distinctive particles, while the Perimac is a very low blood lifetime, so it agglomerates quite early in the liver, while LS08 is in a longer time in the bloodstream. And by using this multicolor reconstruction, the group was able to discriminate the particles in image space over time as well. Yeah, so that's why we have these 2 different colors in the representation. All right, so these are the things I already have shown. So the real-time reconstruction of the bolus within the beating heart. So no gating, no triggering, just acquiring the data, reconstruct the data, and plotting in 3D. That's it. Okay, that's so easy you can make a PhD. Kidding. In the background you see the MR image, and based on the MR image we have, or I have, segmented the different heart chambers and the lungs, and using these different volumes of interest I have used to analyze the MPI signal. And now you can see or appreciate the signal intensities over time for the right heart and the left heart in green here. And you see first in the right heart we can see the signals in phase-wrapped pattern as the ventricle and the atrium will be filled in a different time setting, right? So this is as expected. Same holds true for the left heart. Not only the time signal can be analyzed, we can also analyze these time signals in frequency domain, and we can see that we not only have the heart rate in it, but also the fundamentals or the harmonics of this heart rate, as the beating heart is again not a continuous or a linear procedure, it's also a non-linear behavior, and therefore we can see this non-linearity in the reconstructed time series. Even though we can see, this is not plotted here, but the breathing motion is included in this time series or in the frequency, the power spectra as well. All right, so I've talked a lot about field 3 point with having this, if we are going through the center, having this magnetization, having induced signal and a spectra, and if we are far away from this field 3 point, we stay in saturation, right? And the magnetization does not change over time, and therefore no signal is induced in our receiver. So, and this is not a black and white discrimination as I have shown, depending on the distance to the field 3 point, to the origin to the field 3 point, we have a different fingerprint with odd and even harmonics. So this is field 3 point. So I have also said that there is a different encoding scheme which is called field 3 line, and this looks like this. So we have a field 3 region forming truly a line in space, and this can be moved again similarly to here by a drive field. Now we have a problem, right? So the entire field of view, which is this box, will always be kind of seeing the field 3 line over the time series, and in this direction we don't have any discrimination of the particles. If the particle is here or if it's here in this direction, we can't discriminate, right? So is it pointless? Well, no. And I will show you in a bit. But here in this animation, first of all, I show you the difference between the field 3 line. We have these phantoms here, the point phantoms, and what we do with the field 3 point. We go through this field of view by a rosetta and acquire the signals according to the time. This is just a time course here. And we do the same for the field 3 line, same frequencies, same directions, but now we do not plot the x and y axis, but the angle of the field 3 line and the distance r to the origin, okay? And this is called sinogram, and the sinogram can then be used to reconstruct MPI images. And what we can also see, if all the points are hit by this field 3 line simultaneously, which was in this case at 50 milliseconds, we have the highest peak in the response. That's why, as we are acquiring the full particles along this integral of this field 3 line, okay, which does not hold for the field 3 point, as we do not see all the points at the very same time point. This is why FFL is said to be more sensitive for non-sparse objects. Okay. All right. So diving into field 3 line. So if we have this field 3 line and two objects, and we go through this field 3 line in this direction, we do see time signals or projections of these points along this line. And this projection can then be sorted into our sinogram according to the FFL angle. So this angle represents this column here, and this we can do for each and every angle in order to fill our sinogram. But please keep in mind, we always measure the integral of our field of view along this field 3 line. Okay. So now this is the sinogram which needs to be filled. The red square is just a single measurement, one tri-field cycle for a given point in space. So for this space of the FFL at a specific angle. And now if we have the full translation over the entire field of view, we will measure this blue column. Okay, and by changing the angle, then we measure the next column, and so on and so forth, until the entire cyanogram has been filled. One row, the orange row, is a fixed angle of the field fixed distance to the origin with all the different angles, okay, to make it run and sound. So now we have a phantom which is called P, and we do, please forgive me, the projection is not too good, so we project this, so you can expect the filtry line to be in this direction, and we go through this phantom line by line, and this will be one column in the cyanogram, okay? And this we do for all different angles, stored it into our cyanogram, and now what we can do back projection of the acquired projections to receive our image again. Now this is a bit blurry, that's why we can do a high pass filtering beforehand and do the filtered back projection in order to have a more crystal clear image. Clear so far? Thanks. So, what does it mean in terms of hardware? So we need to generate, first of all, a filtry line. We need to be able to translate this filtry line over the entire field of view. And in order to acquire the full cyanogram, we need also to be able to rotate this filtry line. And ideally, all three capabilities need to come at the very same time to generate, translate, and rotate the filtry line over our field of view. Okay. So for the rotation of the filtry line, you can have two different approaches. First of all, a mechanical rotation of the full gantry. So really mechanically rotate the full magnet step by step or in a continuous mode around our object. More elegant way is to use electromagnetic coils, which are in a specific configuration to rotate the line electromagnetically. Okay. So what is the difference? Mechanic rotation is relatively slow, and mostly it is limited to 180 degree rotation, maybe also 360 degrees, but then mostly you need to rotate back as the cable length is finite and you can't rotate and rotate and rotate. You can overcome this by slip rings, but slip rings in MPI is a nightmare. I can promise never do slip rings to rotate. Therefore, using electromagnetic rotation allows you for a very fast rotation, relatively fast rotation compared to mechanically, and you are not limited. So you can ultimately or infinitely rotate your filtry line as long as you would like and as long as your budget provides for the currents you need to provide. Okay, so again, cyanogram. You need to stick to cyanogram a bit. So this would be the Cartesian cyanogram sampling. So we go through the filtry line in one direction, we change, it's represented here, so we go through the entire field of view with the filtry line, then we change the angle and go back. And this is why we go through the cyanogram in this direction. So you change the angle, you go back, and you go in this meander curve, so stepwise. Stepwise is also again relatively slow, as stepping you need to overcome in a mechanical way the inertia of your entire gantry, which causes a lot of forces. in electromagnetic coils, you need to overcome the impedance of your coils, and therefore you need to provide a high voltage to make these steps very sharp. And again, it is, as it's discrete, it is more likely to be slower compared to other ways. What I've not told you yet, so the translation and rotation is done in my representation by focus fields or shift fields, while we have a third dimension which is spanned up by the tri-field, and the tri-field is in Z direction. Okay, so we have all three spatial coordinates covered in one repetition. Okay. And this is displayed here. So we are wobbling our field tree line at a given discrete angle and a discrete offset through the Z direction, so along the bore line. Okay, so we span up a three-dimensional field of view. So how to increase the field tree based image speed? And I have brought three options which we have. First of all, using faster trajectories. We can use few share and the undersampling, and I will dive into each of them separately. So starting with the faster trajectories. So now what we are doing, we translate our field tree line, and continuously we rotate. Okay, so to minimize the inertia of the system. So this is just, if you zoom in, it's just a straight line. So now sampling of the sinogram is no longer meander curve settings. It's a sine pattern, and now we need to discretize and fill the sinogram accordingly. So here you see it again. So we rotate and we translate continuously at the very same time. All right. And again, the tri-field excitation comes on top in the Z direction. So again, this is how it looks like in sinograms. So the offset in blue and in red scale, the angle, which is over the time series here. And what I normally show is this Rosetta viewing, and here it's always plotted the center point of the field tree line over the time series of our trajectory. Keep in mind, this animation is at a very slower speed compared to the true speed of what we are planning to do in our new MPI system. And we are showing only the zero plane of this field of view. As such, we have the two dimensions for the translation and rotation, and the third dimension for the excitation, the tri-field direction. This means we do not only need to fill a 2D sinogram, but a 3D sinogram. So the excitation direction comes on top, spanning up this 3D field of view. And now we need to find a way to reconstruct this 3D sinogram into image domain. So here you have different options. Either you go with a system matrix, acquiring for each point in space a specific a specific response, and make the standard reconstruction approach. This is very time consuming, as these trajectories can be in the range of 100 to 200 milliseconds, and if you want to do this for each point in space, you will wait for a couple of days to 2 weeks. So that's why we came with a new idea, and before I go into this idea, I will show you why we need to find a new solution. It's not only the time consumption of the calibration, but it's also the fingerprint of the particles. So now if we just have a translation and we have one point in our field of view, this will be the signal response and frequency domain. So we will have most signal in the C receiver and in C receiver in blue, sorry, and in the X direction of our receiver, right? So we only have the frequencies of the tri-field and we have the frequency of the translation. Translation is not shown in this animation. Now I have said that we want to have a continuous motion combining translation and rotation, and if we do so, and we acquire for this point, the spectra look completely different, right? So it is very unsparse. So we have signals in Y channel, we have in X channel, and we have in Z channel. In all three channels we will receive signals. And also here we have much more of the so-called mixing terms, so multiples of and additions and subtractions of the three different frequencies which we inject into our system, namely the frequency of rotation, the frequency of translation, and the frequency of tri-field. And all these three different frequencies will mix our particle response. And this needs to be accounted for during calibration. So there are a lot of calibration techniques out there for filtry line, but these ones are always for static filtry lines. And as already told, the fingerprint for a dynamic scan having rotation, translation, and excitation simultaneously provides you a completely different frequency response of your particles, which need to be incorporated in your calibration. That's why we came up with a new idea. What we do, we take our sine waves, our trajectory, our Rosetta, and we shift this Rosetta, but not in image domain, but in sinogram domain. And we keep our calibration sample at the very center. And by this, changing the trajectory in sinogram domain, we can leverage the response and the signal similarity along the filtry line. And I promise I don't go into depth here, but the major impact of acceleration is in this step here, by replicating the data for a given time point through the entire field of view, as we have a filtry line and the signal is expected to be similar for the entire filtry line extension. Okay, and by this we have A, an acceleration in the acquisition, and B, we have all mixing terms included, and C, we have included the true particle response of our sample. So as we go through the entire steps here, with replication, rotation in time domain, then at the last step we are going to make a Fourier transformation in the time domain to end up with a three-dimensional system matrix again, which we can use for image reconstruction. And the full paper is just under review. So we have performed a lot of experiments. So these are non-simulations, it's really measurements. So we have acquired tediously for each point in space the response of the particles, so the conventional system matrix in 3D. And then we have used our new approach, the sinogram-based acquisition of this of the particle response, and have reconstructed the data. What you can see, these are quite similar in Y and Z, X and Z direction, and in XY direction. Is there a difference? Yes. So we have the same calibration time, but a fourfold of resolution in the XY plane. Okay. What we can, in order to really compare, so at this resolution we would be endless in doing the conventional one. But we need to compare our new method with the conventional one That's why we decided to downsample our high-resolution system matrix to the same resolution as we have the conventional one. By doing so, we have a 60-fold acceleration in theory with the same spatial resolution capabilities. Now, by doing some image reconstruction with the conventional system matrix with, this is not updated, but anyway, with the sinogram-based system matrix, and we do a comparison to the images, they have an excellent similarity, and we do see just noise. And by using this, we can reconstruct quite easily very nice phantoms. All right, the second acceleration would be few share, and this is a very, very short one. So by filling up our sinogram over time, we can just update the sinogram partially. Just the red ones are the new data which are coming in. As soon as the sinogram is filled once, we can update and reconstruct this partially updated sinogram again. And this would be, in this case, a 5 times faster image update, while the data are from a longer period. But still, we can increase the reconstructed time series by doing so by a few share. So that's a very, very short one. And last but not least, I would like to talk about undersampling. Undersampling means that if we consider our trajectory, you can appreciate that we do not hit every point in the sinogram. So this is called sinogram filling factor. It's just the number of the recreated sinogram divided by the total pixel number times 100%. So, is it dangerous to have a non-filled or not fully filled sinogram? What do you think? So, this is a fully sampled sinogram of a phantom. This is a sinogram with holes, so not fully sampled sinogram. So if you do a filtered back projection, is it a good idea? Wow. No. So this is a fully sampled sinogram of this phantom, so we can reconstruct quite easily and quite good. If we add some missing data and do just the back projection, you can't see anything, right? So is undersampling a good way? Well, there are solutions. There are other reconstruction approaches rather than the filtered back projection or iRadon, the inverse radon transform. There is the reconstruction approach ART and SART, and by reconstructing the full sinogram, it is comparable in the image quality. This is a little bit more blurry, but still we can reconstruct the original data set. Using now the undersampled sinogram and reconstruct, we can again reconstruct the original one by telling the algorithm where the holes are and excluding the data, kind of. Okay. And this is a standard reconstruction approach which is used in CT for years to reduce metal artifacts, and this can be used here in NPI as well. All right. So to kind of make a final summary, so field-free point versus field-free line. Field-free point is an intrinsic 1D to 3D encoding due to that it is a point. We can directly reconstruct up to 3D tomographic images by using system matrices. We can do line reconstructions by using the time series as well. We can accelerate this acquisition by having multiple orthogonal tri-field excitations to drive the field-free point on a Lissajous trajectory. And by means of this field-free point, and this is the next talk, we are able to encode in 3D for magnetic fluid hypothermia as well. And due to this point in space, we can sense the magnetic particles at a specific point in space and exclude the rest. And this is very important in the next talk as well. Coming to the field tree line, so it is intrinsically encoding a 1D to a 2D projection, and this projection needs to be reconstructed by using either a sinogram back projection or the ART or S-ART reconstruction approach. And I have shown you a direct 3D tomographic reconstruction by using a sinogram or the sinogram-based adjustment of the height of our trajectory. We have an SNR gain by using the line for non-sparse objects, we can thanks to the line, we always have a very large field of view which we cover, but on the expense that intrinsically it is a projection which needs to be compensated. All right, so you see I'm quite dedicated about field tree point, and I'm quite dedicated about field tree line, and I'm quite dedicated about MPI. That's why it is one of the pillars at Bruker's preclinical imaging portfolio, and we are working hard on providing you with the next generation of MPI system in the near future, but we don't have only MPI, we also provide you with MRI, with PET, with SPECT, with micro-CT, with optical imaging, with inserts, with as a benchtop system or floor-standing systems, and in combinations we have services and software available for you, so it's a one-stop shop for you if you want to deal with preclinical imaging. This is the last slide of my presentation about spatial encoding, FFP and FFL, and I'm open for questions. Either way.
I have I'm sure, a pretty naive question. When you're generating the system matrix, you're taking the time domain signal and you're turning it into a frequency domain. Do you throw out the phase, or is that...
No.
Well,
oh my goodness,
well?
no.
I was going to say, there's a big lot of information that I guess that's just you didn't mention it because it's going into...
So the phase is one of the most important signal compartments in image reconstruction, and especially if you want to reconstruct for binding status or temperature, so MPI-based thermometry. So the thermometry information is, I would say, to 99% in the phase.
Okay.
Yeah. Good question. Yeah.
In the field-free the point-free approach, if I can summarize briefly the overall methods, we have some kind of time-dependent signal which we are transforming or calculating back into spatial domain, and from this we can obtain an image. So basically it sounds for me that like the principle of image reconstruction in MRI. So what is the key point, or the physical key point why we can transfer image reconstruction methods from MRI, where we have the concept of K-space, where we also have like complex data in the time domain into the spatial domain.
Yeah. So we don't have K-space in MPI, and this is unfortunate. And that's why we need to go by different reconstruction approaches. So we can't sample the data and just make a Fourier transformation. That's impossible. We don't have the model for this approach. Instead, we need to acquire the fingerprint for it, and maybe it relates more to the physics of the particles, as depending on the distance to the origin, the particles respond in a different way. In MRI, this would be just a different frequency, right?
So
Or a different phase, which is known a priori. This is not known for MPI, the different fingerprint of the distribution of the harmonics. This is not known, and therefore we need to acquire the system matrix to do the inverse problem solution.
Okay. Yeah. So in MPI we are getting the signal from the oscillating driven field, I guess. And
correct.
in MPI we get the in MRI we get the signal from refocusing spins, which we actually know, but yeah. I have to think about it.
Yeah, we can have a chat in the afternoon as well. Are there further questions? If not, then we are swapping directly or a short. All right, but then give me 1 second. All right. Hello again. My name is still Jochen, and I'm still employee of Bruker. That's why I can skip this. So now we are talking about magnetic fluid hypothermia. Magnetic fluid hypothermia, or hypothermia itself, is nothing new. So hypothermia in itself has been used by the Greeks already for centuries in a systemic way. And the magnetic fluid hypothermia traces back, I would say, according to this paper, at least to the 1950s. Okay. There are a lot of reports out there about what to do with magnetic hypothermia, how it reacts with the body, and how to calculate basically what is going to do, what the particles will do with the body, and how the biological response will be. Well, so far all of the papers are about global magnetic fluid hypothermia, or homogeneous magnetic fields which oscillate, and so you can't have a kind of a spatial encoding in hypothermia despite applying the tracers locally. And this is how it is done for years now. So, but to start in the basics, so what is magnetic fluid hypothermia? So we are using, again, our precious magnetic particles, so iron oxides, for instance, and by applying an oscillating magnetic field, we again drive through our nonlinear magnetization response. And now what happens, and then this is different representation as I have proposed in my previous talk. Now it's not a single nonlinear curve, it is a hysteresis curve. While hysteresis curves are in technical devices normally a very bad phenomena, as the area spanned up by this field by this hysteresis consumes energy. And normally we want to be efficient, and we want to have get rid of this, but in magnetic fluid hypothermia we exactly exploding this area under the curve as it translates. So the particles itself, they absorb the energy and they will transfer this energy into thermal energy. And this can be seen here by a thermal camera which has been pointed toward the phantom, where we have placed different concentrations of one single particle type. And as you can see, they heat up significantly by, in this case, it's a 700 kilohertz oscillating magnetic field. And I have cut it off the color bars, but the red one was 60 degrees Celsius, something like this. But don't nail me down read the paper, then you know it. And what we can appreciate, the temperature is different for the different vials, and this is caused by a different concentration. This is the highest concentration, therefore we have a high temperature increase. This is the lowest concentration, therefore a lower temperature increase. And this is already one of the first problems of hypothermia. We have a dependencies on the concentration. And for standard magnetic fluid hypothermia, we don't know the concentration in the tissue, right? And I will come back to this again. So now, what we can measure with some devices, the magnetization response, so the hysteresis curve for various frequencies, for 12 kilohertz, for 25 kilohertz, for 300 kilohertz. You decide measuring the area under the curve to calculate the specific absorption rate. This you can do also for different field amplitudes of the excitation frequency. And as you can see, depending, the higher the excitation amplitude, the larger you extend to the saturation phase of your particles. So, and as said, the area under the curve is proportional to the specific absorption rate, which we want to exploit in magnetic hypothermia. So if we plot this over this very same data as I have shown already, so about the frequency and the amplitude, you see for low frequency, so 12 and 25 kilohertz, they do not respond in a very strong way in terms of hysteresis, while for high frequencies, the 300 kilohertz, the SAR, so the area under the curve, is going through the roof. And this is exactly what we're going to use in magnetic fluid hypothermia. So biological effects are that the local temperature in cells, the increased temperature, could enhance the reactive oxygen species, and therefore could go for cell death. This is for tumor treatment very sensitive or very beneficial, but there are different applications where I go into detail in a bit as well, where we don't want to have the cell death itself. So about Theranostics, so what does it mean? Well, we have the diagnostics somewhere in the body, and then we need to have kind of a therapy. For years we had to cut open and remove, or we have systemic application of some drugs. We need to swallow some drugs, and this will be distributed in the body. So there is a very inaccurate and a very inefficient way. So there are a couple of main challenges in magnetic fluid hypothermia. So first of all, we need to focus on the thermal dosage. We need to have a uniform thermal dose in a controlled area, and we need to monitor what's going on in the body. And these are so far unsolved topics. I have a different representation of the pitfalls. So we want to increase the dosage, but we want to be specific and non-invasive, and best we would like to control and to supervise what's going on. So there are some stretches which we need to do, and this is what we try to solve in our new product. So, and this leads me to the terms from imaging only to Theranostics. And Theranostics, as already said, it's a combination of therapy and diagnostic in the single device, coping with the two different perspectives. There is a recent paper out from the US, and this review shows that it's quite that there is a quite huge potential combining different magnetic nanoparticle mediated imaging and therapy devices to have this theranostic approach. Okay, and as promised, there are different applications which we foresee in magnetic fluid hypothermia. It is not only tumor treatment, but it's also to stimulate the body to overcome some biobarriers, to have localized therapy, to have targeted drug delivery, to provide the therapy supervision, to stimulate the immune response, or to increase permeability. So what the heck are we talking here in an MPI session about hypothermia? Well, in MPI, as already stated, we acquire the distribution of iron oxides in space. We can have this in real time, can have this in high resolutions, we can extract physical properties like flow, but we can also, and this was one of the last questions, thanks to the phase information of the particle response, we can not only reconstruct the particle distribution in space, but we can also detect or reconstruct for thermal changes. So to have a thermometry, MPI-based thermometry within the body without any cut open to put in any temperature sensors. The particle itself, or the particles itself, are the thermometer, and we can read out this just by magnetic fields. Okay, and reconstruct it in 3D or 4D, time resolved 3D. As already told, in MPI we are using a filtry point or filtry line to encode the signal, and the very same procedure we can use for the magnetic fluid hypothermia, as only particles which will be hit by the filtry point will be contributing to the thermal dose. So, as in the previous talk, there is a filtry line, there is a filtry point, which is better for magnetic fluid hypothermia, for localized magnetic fluid hypothermia. What do you think? So what is more beneficial, filtry line or filtry point for a targeted hypothermia? Filtry point, yeah. Yeah, exactly. As it has intrinsically a single point in space or a very tiny field of therapy, which will be contributing to the overall dose. Still, you could use a filtry line by changing the angle and to superimpose the full deposited energy in the single point. So it is feasible. Similarly to radiotherapy, which you do from different angles to superimpose the individual doses. And you can spare some areas in the body which will never ever tolerate any signal increase. This would be also possible by a filtry line, but it's more elegant to use a filtry point. Okay, as said, so having particles which will be hit by the filtry point, we will go through the magnetization curve or the hysteresis at the end, and while particles far away or objects far away from this filtry point stay in saturation, so we do not go through the magnetization curve, and therefore the area under the curve is zero, and therefore no energy will be deposited at this point in space. And similarly to the filtry point imaging domain, if we move the filtry point with a high frequency in space, then we span up a very, very tiny field of therapy in the 3D object. Okay, and this is basically also a hands-on here. So if we have this filtry point, which is, first of all, we start in this condition. So without any external magnetic field, and we have an oscillating magnetic field, all the particles will react. I don't know if you see it. So they all react to this external magnetic field, right? So the energy which we will deposit will be distributed in the entire volume. Now by having this field-free point, okay, so this will be located just at the center where these two permanent magnets cancel each other. Then I do the same, then all the particles will be blocked by this external magnetic field, and only the particles at the very center will react, and therefore only at this region the energy will be deposited. And feel free to come and play a little. Right. This was this. Yeah, this one. So now talking about targeted or localized therapy. So by leveraging the position of the field-free point, we can decide where to heat in our phantom or our object. This experiment has been performed in a similar system like here in Prague, which you see in the hands-on session, where we can adjust the selection field. So here the selection field is on and the field-free point is moved by the focus fields. And in the very last session, the gradient strength was set to 0, and therefore all the particles will heat up simultaneously. All right, so the question will be most probably, how precise is this targeting? And by making some calculations, this would be the point spread function of a hypothermia in X and Y direction, and in Z direction, or in this direction. We have plotted the specific absorption rate. And if we look from the top, so this is the excitation direction, you see that we have a very, very precise or a narrow point spread function, while in the other direction it fades a little longer to react on the external magnetic field. So a combination of gradient and the magnetic fluid hypothermia field. But still, it is concentrated on a single tiny field of therapy. Okay. So we also need to talk about biosafety limits, right, or biosafety considerations. So in different RF ranges, so radio frequency ranges below 1 kilohertz, you will stimulate nerves, so your patient won't like it if you apply these frequencies. If we crank up the frequency, you can provoke tissue heating, but non-specifically. So by just inducing eddy currents in the tissue, then you will heat up the tissue entirely. And by increasing the frequency further, we are able to heat up the particles itself. Okay, and this is just as with the increasing frequencies, this hysteresis curve will span up.
But if we increase the frequency, do we then not have the effects of the upper two? Or
yeah, you need to consider all the three ones to have to minimize the unspecific ones, but to increase the specific ones. That's why I bring it up here, so to not only concentrate on the wanted effect, but also to the unwanted effect. And then there are also some biosafety limits provided in different papers for clinical, for full body, small parts of the body, or preclinical. And you need to consider which amplitude and frequency you select in order to stay in the limits of choice. And this, again, this is not related at all to the effect which we want to do. Okay, this is without any effect of the tracer material. This is just a multiplication of the applied external magnetic field multiplied with the frequency obtained or used. Okay. So now we can leverage different things in MFH applications. So from an instrumentation point of view, we can change the selection field gradient, and by increasing the selection field gradient, the field of therapy will shrink. The magnetic fluid hypothermia amplitude will also, first of all, change the excitation and the span of this hysteresis, and therefore will have a very high effect of the specific absorption rate, but it also changes the field of therapy. The frequency of the applied field will have an effect on the excitation and therefore the specific absorption rate. And on the tracer side, we need to think of the hysteresis itself. So increasing the magnetic behavior and increasing the area to have increased the specific absorption rate, but it also has an effect to the field of therapy, as I have shown in the point spread function. So having a larger area, it is better in terms of SAR, but it also has an increased field of therapy though. The concentration for sure is a huge leverage of the SAR, and the binding status of the tracer will have an effect. And well, this is for sure unknown in normal applications. Okay, so we need to consider how to track the dosage applied. And here we go. This is the phase, which is, so this is one frequency component of a system matrix, and you see the rotation of this frequency over the phase, and exactly this is according or differently for different frequencies, different temperatures. And this is what we leverage for reconstructing thermal images. And this is a phantom experiment, 2 vials, while one was heated with a laser and the other one was not touched directly with the laser, and we could reconstruct the temperature increase by means of the tracer response. So going into some applications, so we can now, as we combine MPI and hypothermia in a single device, we can swap in between the different modes. So we can start with a hypothermia session, then we swap over to make an image, and then we do another hypothermia session. And as we have the selection field gradient, we can also select at which point in space we want to heat. And by having 3 different phantoms in one direction, we selected the left particle vial to be heated up locally, and we have reconstructed the temperature of all the 3 different vials. And so this is a thermo camera, the full lines, and the dots is a reconstruction by MPI. So there is a strong relationship between the 2 different signals, indicating that MPI could have a huge impact for future hypothermia. As said, depending on the area in the gradient, either the particles will be heated up or they are unaffected. And this has been done here, again in a reconstructed image. So different time points, different positions in space heated up, and all done in a single device. And by switching off the gradient, all the particles within the field of therapy is, so to say, infinite. So the size of the hypothermia coil. What do we need to have? We need to know the anatomical reference. Where do we want to go with the therapy? We need to have the quantitative tracer distribution to plan for the therapy, as concentration is the key of the specific absorption rate. We want to have a localized energy deposition, and we can leverage now the MPI-based thermometry, and therefore calculate the thermal dose over the time course. And by having this, we can have a closed hypothermia control loop in the end. So, and this is what our vision is. So, combining magnetic particle imaging, magnetic fluid hypothermia, and additionally, for the full perspective, for the anatomical reference, combining with computed tomography, and in the base or in the overlap of all three, it stands for Theranostics, and this is where our new system will be located. So having all these different functionalities in a single device. So just a rough sketch, and you can hate it or not. I'm really bad drawer, and this was just in a night session. So what we can do, we can in CT, we can just scan the animal from tip to toe. Then we plan for where we want to do imaging. To have the MPI tracer concentration. Then we are planning where to heat up in this concentration difference, and only locally we treat the tracer. Then we swap over to MPI and do the full tracer temperature map. And by combining all the different data, we end up with a theranostic data set. So this is I think a representation which could stick to your minds, even though it's quite ugly. But anyways, the idea is, I think, crystal clear how to combine and how to leverage the different modalities. So finally, so what we can do, MPI tracer concentration or distribution, CT morphology, we plan for the therapy, we encode the hypothermia by the selection field, we make the image-based thermometry, and then feeding back and adapting the therapy in order to not extend the limits we want to have. So just to show you that we are working hard on the Theranostics, we have a lot of research ongoing. First of all, we want to open up the blood-brain barrier to tackle brain tumor, not by MPI or by hypothermia, but we use hypothermia to increase the permeability of the blood-brain barrier to deliver drugs into the brain tissue, and this only locally, as the blood-brain barrier currently does block the pharmaceutics to enter from the bloodstream into the brain tissue, and therefore we want to increase the permeability to get the drugs into the target region. This we have shown with different phantoms already with a thermometry and localized therapy, and we have performed, and this is really a unique experiment so far, an in vivo study where we have scanned the baseline, then we have applied hypothermia and tracked the temperature, in this case by a sensor in the brain and the body. It's not MPI thermometry, to be clear. Then we have added a systemic bolus in the tail vein and have tracked the temperature over time without hypothermia. Then we have cranked up the hypothermia amplitude and have provided a second bolus. So this was only to saturate the liver, and the second bolus was the one which we want to have to increase the temperature locally in the brain. And as you can see, the brain temperature increases, but very little, just a 0.5 Kelvin, which is not sufficient to open the blood-brain barrier. And the third hypothermia session resulted in the very same setting. So this learned us quite a lot, so that the physiological properties must not be underestimated. So we have blood flow, we have temperature regulations in the body, and therefore we need to find different solutions to come to this vision, and we are working currently on these solutions to get a higher increase of the temperature locally at the blood-brain barrier. Secondly, we are in a consortium funded by the Bundesministerium für Wirtschaft und Klima, in a consortium with BioNTech, with Fraunhofer Physikalisch-Technische Bundesanstalt, SEMO Center in the University Hamburg, for getting novel strategies for mRNA-based theranostics. And here, what we do is precise calibration and thermometry. We do work out new workflows for these theranostics. We build new in situ magnetic fluid hypothermias inserts, and to stack everything together in a multimodal theranostic platform. I have brought some application notes about theranostics. Please feel free to take one for your reference. And this is the final session here. What we are looking for is not only providing you with new instrumentation, but the full perspective from software to services and tracer. And that's why we have linked with Micromod to also have a new tracer in our portfolio together with Micromod. And this will be Sinomag Pro, which is an optimized tracer material for in vivo settings with a low endotoxin content, optimal for in vivo studies. Yeah, and we are working with the Fraunhofer Institute to get hypothermia up and running. You see the prototype here, and that is what we are going to do with the new development of a new system. So it's fully application driven to optimize the access for the tracer environment. So to tackle the tracer binding status, MPI based thermometry and viscosity. You will be able to have the morphology planning by the in situ CT. We have reworked our complete electronics to have a much better and a highly improved transmit-receive path to ultimately allow for molecular sensitivity, increasing the sensitivity for you guys, having lower applied dosage of the tracer or a higher SNR. And last but not least, we have developed a magnetic field generator capable for FFP and FFL at the very same not in the very same time, but the same magnetic field generator can provide both modalities or different modes of the field gradient, and it allows for fast rotation and therefore a high temporal resolution for MPI. Yeah, and for sure, the last piece is the in situ theranostics, so an hypothermia insert into the system, so you don't need to move your animal from system A to system B. You can do everything in one device, and you don't have to fiddle around with tracer and different labels to merge your data. So everything is covered in a single device. Yeah, so it's called it's kind of a tree-modal system at the end. So, yeah, just want to make sure that's not only me who is working on that, it's my team, it's Timo, Oliver and Serhat in Ettlingen, and a bunch of people more from the central R&D who are working quite hard to provide you with the latest update of a new tree-modal system. Yeah, with this, I would like just to mention there is a podcast. It's available in German only, but in an English subtitle. So if you want to hear about theranostics and my vision about it, feel free to listen to it. With this, I would like to thank you for your attention, and I would like to thank our customers, Kapi, for inviting me here for these two talks, our cooperation partners and our funding sources. And I would like to thank you guys and girls for providing your time. Thank you.